Right now we're going to look at resistance. Resistance is based on three qualities of that material. The first thing we need to know is how long is the stretch we're trying to push those electrons through. We're trying to push that current through how long of a stretch, and what is the cross-sectional area of that stretch? Are we trying to push all that current through a big wire, or are we trying to squeeze it through a small wire? And then the last thing we need to look at is the resistivity. How resistant is that material to the movement of electrons? So length is the first one. So the longer the length, the higher the resistance, and you'll notice it has a one-to-one relationship. Meaning if I double the length of my wire, it doubles the resistance of that wire. Now, cross-sectional area, you'll see, is on the bottom. So if I increase the cross-sectional area, it decreases the resistance. Now, this one's a little different because typically we don't talk about cross-sectional area for a wire. We typically talk about the radius or the diameter of the wire. And so what we need to keep in mind here is that that cross-sectional area is typically going to be that of a circle. It's a circle when looked on the end, and we get pi r squared, meaning we have a squared term there. So if I take a wire and I double the radius, that's multiplying the bottom here by 2 squared. So I have 2 squared on the bottom. That means I'm dividing by 4. So by doubling the radius, I actually get 1/4 the resistance. And then the last thing, resistivity. This is based on the material itself. This is measured in ohm meters, how many ohms per meter. You will have to get this from a table. It's kind of like the mu constant, the coefficient of friction. It's just something that is measured, and then we use that. So just Google it if you need to know any of them. The smaller that value, and these values are ridiculously small, by the way. Copper, for instance, what was copper? Copper is 10 to the negative 8th ohm meters kind of range. So these values are exceedingly small when I say small. So conductors have small, insulators have large values. So the top one, so let's talk about this for a second. The top one is silver. Silver is the best conductor. So if I wanted to have the most efficient electronics, I would want to make all of my wires out of silver because I'm going to lose the least amount of energy as that current flows through that wire. Now, believe it or not, Mr. Foster is concerned about efficiency, but my house does not have silver wiring. Why not? Yes, because it's expensive. So Mr. Foster went for the second choice, which was copper. Okay, why didn't he go for the third choice? Again, super expensive. So we're going to stick with copper. So if you go into your house, don't tear the wires out of the wall, please. You'll notice there are different colors possibly of wires, depending on how new your house is. So those colors tell you how thick the wire is. So I don't know if you can see this here. Let's zoom in quick. All right, so we've zoomed in on these wires. And so what I have here is I have the 3 typical ones that you'll find in your house. So I have the 14 gauge, the 12 gauge, and the 10 gauge wire. So what we have then is different amounts of current can flow through each of these safely. And the idea is you just have larger pipes if you want to send more current, similar to the plumbing in your house. Now, at some point, you might want more than these can handle. So this can handle up to 15 amps. So we can actually fit quite a bit of stuff on 15 amps. Now when it comes to kitchen appliances that start to take a lot more energy, maybe we're going to need to pump that up to 20 amps of coverage. But then what about those bigger appliances? And so that's where this comes in. So this is what you'd run your stove or your dryer on. But then maybe you want to add on to your house, and so you want to bring a lot of power out to a new section of your house. So you would need a big wire, and you'll notice that this wire is no longer made of copper, but it's now made of aluminum. So even though copper is a better conductor, when we're talking about transmitting big amounts of energy, we typically switch to aluminum just because it's cheaper. It's also much lighter weight. So since I need these big, thick wires, I'm going to have to switch to aluminum. Now, when I switch to aluminum, aluminum's not as good a conductor. So what I'm going to want to do is I'm actually going to want to make those wires even bigger than they would be if they were copper. Now, the other thing is you might have a transmission line. Those are the ones you see on the power poles. They are going to be very thick. And usually they'll be many different wires kind of put together. Okay. Now, why would you want to use aluminum if you're a power company? Now, one of the big reasons is aluminum's a lot lighter weight, and if you're going to string these things up between power poles, lighter weight means they're easier to deal with. Now, I got out my USB cord here, and you'll notice that it has probably either aluminum or maybe even a stainless steel on here. So why did they choose to use aluminum instead of, say, copper? This isn't a big space. Why use aluminum? And if you go to the store, they might even say, you know what, you need to use gold. And you might be thinking, oh yeah, gold, it's a better conductor than aluminum, but why wouldn't you use silver or, say, copper? Both are better conductors than gold. Why do they want you to use gold for those connectors? So the reason is, and I'll spoil it here for you, the reason is you'll notice that this copper here is kind of tarnished. It's not as shiny as it used to be. And if I was to scrape this clean, it would get this bright color on it. And so what happens is things like copper and silver, they actually oxidize, and silver tarnishes. You might have heard that term. And so it doesn't keep its shine, and you get this layer of oxidized material on the surface, and it's not as good of a conductor. So for things that you're going to kind of connect together, you want things that won't tarnish. For this wire, if I cut it open inside, it isn't tarnished inside, and that's where all the flow is happening. So I'm okay with that. It's just at those connecting points is maybe where I'm going to want to spend that extra money to get those things that won't tarnish, or in this case, I'm just going to be happy with aluminum or stainless steel. Let's go ahead and take a look at an example next. All right, now that we've seen what kind of wires to use, let's do an example. So the example is number 6, right there on page number 5 of your packet. So take a second, hit pause, read the question. All right, now that you've read the question, let's go ahead and solve it. So we have that 14 gauge wire. It tells us the diameter. Of course, we're going to need to change diameter to radius, and then we're going to need to get millimeters to meters. It also tells me the length of that wire, 2 meters, and it tells me it's a copper wire. So I need to look up online the resistivity of copper. I'm going to give it to you in the homework, though, so don't worry about looking that up for the homework. I need to look it up. It is annealed copper. Annealed copper is the word we use to tell us that it is the copper we make a wire out of. It's not just like raw copper. It's been stretched into a wire. And so I look it up, and it's 1.72 times 10 to the negative 8th ohm meters. So let's go ahead, plug that in our equation, and see the resistance value we have. So plug in my numbers. So I have the resistivity 1.72 times 10 to the negative 8th times the length, which was 2, divided by the cross-sectional area. Now, because they told me it's a wire, I can conclude that that is making a circle. And so I'm going to need to make this substitution. So I have pi times r squared. This is my r term up here, 8.14 times 10 to the negative 3rd meters. Go ahead, plug all that in, and be extra careful with those 10 to the negative 8s, 10 to the negative 3rds. Oops, that is a squared on the bottom there as well. Make sure that you get that stuff typed in correctly into your calculator using parentheses where appropriate. Maybe the ones that you might forget are the parentheses you need around that pi and that r squared on the bottom, so they both get divided. When you get that all done, you should get a value of 0.165 ohms for that resistance there. And so yes, the units, I don't know if I said it earlier, for resistance is ohms. That's spelled out O-H-M. There you go.